Section 5.3, Medians and Altitudes in Triangles. By the end of this lesson, you should be able to identify medians and altitudes of triangles. You should also be able to apply properties of medians and altitudes of triangles. To get us started, we should talk about what the median of a triangle is. The median of a triangle is going to be a segment whose endpoints are a vertex of a triangle and the midpoint of the opposite side. Let me move this over so we can see the diagram a little bit better. So I'm going to go ahead and highlight the medians of this triangle on the diagram. And as we can see, they all will have one endpoint as a vertex of the triangle. Let's say it's point B. And it's going to have the other endpoint as the midpoint of the opposite side. We did a sketchpad activity in class, and in the sketchpad activity you were asked to construct the medians, and they asked you to do the same thing by connecting the vertex with the midpoint of the opposite side, and that's how you construct the medians. You know it's a median because it has these congruent tick marks telling you that it's being connected from the vertex to the midpoint of the opposite side. Now, all of these medians are concurrent. They all intersect at the same point. And that point of concurrency is called the centroid, which brings us to our theorem. Now, in the sketchpad activity, we were able to see that, let's click outside here, that when we've constructed the medians of the triangle, we can move this around. They're always going to be concurrent at the centroid. But we were asked to find out something about the measure. So in this one, we were asked to find out what is the relationship between this measure from the centroid to the midpoint, so this segment CEF, and this other segment, the other part of the median, which goes from the centroid to the vertex, BCE. Right now, we see that CEF measures 3 centimeters and BCE measures 6 centimeters. You're also asked to make a table of values as you're going through this. And in our table of values, some of these values are, like we have here, that CEF is 3 when CEB is 6, CEF is 4 when CEB is 8, CEF is 1.5 when CEB is 3, and so on. So from this, we're noticing a pattern, and that pattern is that CEF is going to be half as long as BCE. In other words, this centroid is going to be a certain distance from the midpoint, and that distance is always going to be doubled when you connect that or measure the distance from the centroid to the vertex. Heading back to our notes, we have a theorem that has to do with the centroid. Now, earlier, our theorems that had to do with the points of concurrency of our special segments were always equidistant. This one's different because it's not going to be equidistant, but there are some special measures that we can notice. And the concurrency of medians theorem states that the medians intersect at a point, and we know this point's called the centroid, and it's 2/3 away from the vertex and 1/3 away from the midpoint, which you can see from what we had just noticed in the sketchpad activity. So how does this play out in the different types of problems we're going to have to do? Well, let's say we're given that T is the centroid of triangle QRS. Knowing that that's the centroid, we know that we have congruent, that we have the medians drawn here. And let's see here, let's grab a pen. We know that these segments are going to be congruent because the medians are formed by taking the vertex and drawing a segment that connects to the midpoint of the opposite side. So if all these points located on the sides of the triangles are the midpoints, we know that they bisect those sides. What they also tell us is that TU is 7. So knowing that TU is 7 is helpful to us. And when we're trying to solve a problem like this, I recommend that you always solve for all 3 parts of your median. So for us, we're going to be taking a look at QT, TU, and QU. So we know that TU is 7, and we can record that. Looking at this, TU is the segment formed by the centroid and the midpoint. And we know that that is going to be half as much as the segment formed by the vertex to the centroid. So we know that QT should be 14. Then what we can say is altogether, QU, the entire segment, that median would have to be the whole. And we can just add those parts together, and we know that QU is going to be 21. Now going back to our theorem that we had just talked about, we can see that TU is going to be 1/3 of the median, which is 21, and we can see that QT is 2/3 of the median, which is 21. And that's how that theorem looks when we apply it to a problem. Next, we have altitudes of a triangle. And altitudes of a triangle, it's good to know what they are. Altitudes of a triangle are these highlighted segments. And the altitude is formed by the segment that starts out at the vertex and is perpendicular to the opposite side. So as long as it starts at the vertex and is perpendicular to the opposite side, you can say that that's going to be the altitude. The altitudes have a point of concurrency, and that point of concurrency is called the orthocenter. The nice thing about this is that our orthocenter doesn't have any special measurement qualities like we've seen before. So there is no special theorem that is associated with the altitudes of a triangle. All that you need to know is that they're concurrent, and their point of concurrency is going to be called the orthocenter. So a problem that you might be asked to explain your answer to is the orthocenter for an isosceles triangle always located inside the triangle? Explain. Well, looking at the sketchpad activity for our altitudes of a triangle, we would be able to see that I've drawn in these altitudes, so they're perpendicular to these opposite sides and so forth. And this intersection point in the center is going to be our orthocenter. Now, if we move our triangle around, we notice that the orthocenter isn't always going to be inside of the triangle. And to help us with that, we can measure these angles. So I know that measurement of angle B is 43 degrees. The measurement of angle C is 72. And the measurement of A in this case is 62. So right now we can classify this as an acute triangle because all of our angle measurements are acute angles. So moving this along, I'm noticing right now it's on the triangle. And looking at the angle measurements, we can say that this is a right triangle because angle A is a right triangle in this case. Moving it around, let's try to see what we can do to get it outside. Now it's outside of the triangle, and looking at this, it appears to be that C is obtuse, making this an obtuse triangle. So going back to our notes, is the orthocenter for an isosceles triangle always located in the triangle? Let's take a look and see what that meant. So it's an isosceles triangle always located inside the triangle. Well, we know that if, and let's go ahead and mark this, that if it's a right triangle, then we can say that the orthocenter is going to be on. And we also know that if it's obtuse, then it's going to be outside of the triangle. So when they say is the orthocenter for an isosceles triangle always located in this triangle, we can say no because of this. And that concludes our lesson, which means it's time for our joke. And our joke is, what do you call a snowman in the summer? Well, you call snowman in the summer a puddle.